So what I want you to think about first is the word asymptote. Okay? Now, we talked about it at the very, very beginning of school. Do you remember us talking about that? And I said, we'll talk about it later. Well, today is later. Okay? Before we start talking about what it is, though, I have to set some ground rules for the word asymptote. Okay? First of all, we're not going to abbreviate it, because even if we did, it would be ASY and not what you want it to be. Okay? Second of all, we're not going to unnecessarily stress the first syllable of the word asymptote. Can you handle that? Third and last, I want you to refrain from walking through the halls telling each other you're going to kick each other in the asymptote or beat each other's asymptote. Okay? I don't want to get called into the office again. Because somebody said it in front of a non-math teacher who thought they were cursing, and I got called into the office because when the kid got called in the office, they were like, Miss Kingston taught us. Oh, please. You could have explained it a little bit better than that, right? So, can we keep that in the classroom? In here, like in the math classroom, right? Okay. Now, you guys know I'm being silly, right? Because we're not going to say that anyway. But I do every once in a while when we're joking, right? Okay. But for serious, not in front of non-math people. Okay? What is an asymptote to begin with? Well, look with me for a second on my calculator. You don't have to get yours out if you don't want to. But I want to show you real quick. We are starting rational functions. Right? We're starting this section on rational functions. What does it mean for it to be a rational function? Where is the variable? Where is it? It's in the denominator, right? The variable's in the denominator. Look what shape it makes. Doesn't it look like there's two parts of this graph?
Yes.
There's not. It's just one graph. Now, it does look like there's two parts. I agree with that. Okay? But that's because there is a vertical asymptote and there is a horizontal asymptote. Okay? So what actually lives right here? On the x-axis, what lives there? Nothing, right? Nothing lives there because what happens if I put in a 0 for x? That's this one right here, right? What if I put in a 0 for x? I get a 0 for my denominator. Am I allowed to have that? Are you allowed to divide by 0? Ever? Yeah, the only person I know that can divide by 0 is Chuck Norris, and he's not in this class. Right? We can't divide by 0. When a situation occurs that we end up dividing by 0, that's one of the ways that an asymptote shows up. Okay? That's actually a vertical asymptote. Okay? We're going to talk about how to find them in just a second, but I want to make sure you know, if I graph this by myself, what I'm putting right here is a dotted line. I use a dotted line to represent an asymptote because I want to make sure that I know nothing can happen there. Do you see that there's also a dotted line on the x-axis? And again, we'll talk about how to find those in just a second. We're actually going to talk about horizontal asymptotes first. Okay? But nothing can live there. That's part of the reason why I draw a dotted line, because even the asymptote's not there. But I draw the dotted line to tell myself nothing is there. Does that make sense? Okay. So what I want to do is I want to jump to the back of the first page, because remember we're trying to save some time here. Right? I'm going to jump to the back of the first page, and if we had time, we would go around the room and everyone would fill these in. Oh, we don't have time for that. You know that. Okay? So what I'm going to do is I'm going to fill it in for you, and then we're going to talk about it. Is that all right? Okay? I'm going to say it out loud, but I'm also going to write it. So if you want to listen to me say it out loud, you can write it as I'm saying it. Does that make sense? Okay, so this first box right, in order for you to write it as I say it, you kind of have to be holding on to your pencils. Okay, 0.998. The next one is 0.999. And then 0.9993. And then 0.9995. Okay, I'm going down. So negative 1.67. Negative 1.668. Negative 1.668 again. Negative 1.667. Okay, the next table is 0.0017, 0.0008, 0.0006, 0.0004. Okay, and the last table in this column is 0.00125, 0.00062, 0.00042, and 0.00031. You got all those? Okay, top of the next column, ready? 0.5027, 0.5013, 0.5009, and 0.5006. Okay. Next table is 2002, 4002, 6002, and 8002. The next table is 2.508, 2.504, 2.503, and 2.502. And the last table on this page is 500, 1,000, 1,500, and 2,000. Okay, does everybody have all their tables filled? Okay, now here's what I want you to do. Okay, on every single one of these tables, X is increasing by a lot. It's not going 1, 2, 3, is it? It's going 1,000, 2,000, 3,000, 4,000. So it's getting bigger really quickly, isn't it? Okay? As it's getting bigger really quickly, I need you to notice some things. First of all, I want you to circle 1, 3, 2, and 6. These are the ones that we're going to look at first because these are the easiest to see. Okay? As X is getting bigger, what's happening to Y's? Is it getting bigger or smaller? Bigger. Okay? Is it getting closer and closer and closer to some number? What number? To 1, right? Isn't it getting closer and closer to 1? First of all, do you think it's ever going to get there? It won't. Right? Now, calculator-wise, it will eventually get there because calculator only has so much room, right, that it can have place values and things like that. But I want you to know it's getting closer and closer to 1. Okay? For the record, when it gets closer and closer to something and it never gets there, that's called a limit. And that's a pretty important idea in pre-calculus and calculus. Okay? So if you're heading there next year, I want you to think about that. Or just know, at least know that word. Okay? What about this? Is it getting bigger or smaller? So 0.67, then 0.66. That's smaller, right? But is it getting closer and closer and closer to some particular number? Well, 0, if it's getting smaller, 0's up here somewhere, right? And it's getting smaller. It kind of looks like it's getting closer to -2, but it's actually a little bit closer than that. It's actually -0.1, sorry, -1.66666666. It's repeating, right? What number is that? Isn't that -1 2/3? Isn't that also the same as -5/3? Yeah? Look at number 2. Is this getting bigger or smaller? It's getting smaller. What number is it getting closer and closer and closer to? 0.5, right? 1/2. Everybody okay with that? Is this number getting bigger or smaller? Smaller. What is it getting closer and closer to? 2.5. Is that the same as 5/2? Yes? Okay. So, oh, dang it, I wrote it in the wrong place. Sorry about that. 5 halves. That's where I wanted to write it. I want you to look at the number we just wrote over here, and I want you to look at the equation. Look at the equation. Can you see the number we wrote over here in the equation somewhere? Where is it? Do you see it? Yeah? Now, you know that I didn't circle every problem. I just circled 1, 2, 3, and 6, right? So there has to be something about different about 1, 2, 3, and 6 that we have to notice. Okay? Look, please, at the exponents. What's this exponent? 1 and 1. What's this exponent? 1 and 1. What's this exponent? 1 and 1. What's this exponent? 2 and 2. So what's true about the exponents in each individual problem? They're the same. Do you see that? The same in the numerator as the denominator. I'm talking about the highest exponent. You can't really tell that in this problem. I guess you can in this problem, right? Because there's an exponent here, but I'm really concerned only about the highest exponent. Do you remember what that word is called? The highest exponent? Do you remember us talking about the degree? And that's the highest exponent when we talked about polynomials. Okay? So if the degrees are the same, where do I find the horizontal asymptote? It's at the front, right? Y equals negative 5/3. Y equals 1/2. Y equals 5 halves. Because here's the deal. Do you want to have to make a table every single time, or would you rather think about like shortcuts? You okay with that? Now would you please look at 5 and 7. As x is getting bigger, is y getting bigger or smaller? Smaller? What's it getting closer and closer to? Yeah. Number 7, as x is getting bigger, what is y doing? And it's getting closer and closer to what? 0. Now you know we're going to be looking at exponents. Look at the exponents in this problem and tell me what you notice. Are they the same, first of all? No. This one's a 1 and this one's a 2. This one's a 0 and this one's a 1. Where's the bigger exponent? In the bottom. When the bigger exponent, when the degree is in the denominator, y equals 0, as proof by our table. But again, we don't have to make a table every time. We want to notice that our degree is in the denominator. And when our degree, our highest exponent, is in the denominator, y equals 0. That's where our horizontal asymptote is. Okay? Now, last one. 4 and 8. Tell me what you notice about those exponents. The degree is in the numerator. When the degree is in the numerator, look what's happening to the y values. Is it getting bigger or smaller? Bigger? Is it approaching anything? Is it getting closer and closer to some number? Or is it just getting bigger? Then there's not one. When the degree is in the numerator, there is not a horizontal asymptote. Does everybody understand that? When the degree is in the denominator, where is the horizontal asymptote? Y equals 0. When the degrees are the same, where is the horizontal asymptote? In the front, right? Do you remember what those numbers are called? Because I'm trying to teach you concepts and then I'm trying to teach you vocabulary, right? So right here we're talking about the leading coefficients. The leading coefficients, the leading coefficients, the first coefficients. Does that make sense? Turn to the next page, please, and let's make sure we're confident with our vocabulary then. First of all, we need to look at the exponents. You need to find the greatest exponent used in the numerator and the denominator. Very good. In each, the greatest exponent is called the Very good. So when the numerator is greater, there's not one. When they are the same, we have the leading coefficients. Y equals the leading coefficients. And when the denominator is greater, y equals 0. Does that make sense? So look at problem number 1. We're going to do number 1 together so you know how to do 2, 3, and 4. You ready? First, look at the exponents. What is the degree of the numerator? 2. What is the degree of the denominator? 2. Compare those two numbers. They are the same. If they are the same, where is my asymptote? Y equals 3/5. If it said numerator is greater, if this is a 3 and this is a 2, what would I write right here? None. And if the denominator was greater, if this was a 3 down here and this was a 2, what would I write right here? Y equals 0. Now, I'm being picky when I say that, right? Because sometimes you guys said, oh, it's 3/5. And what did I say? Y equals 3/5. And then when we talked about this one, I said, where is the horizontal asymptote? And you said, at 0. And I said, y equals 0, right? Because remember when we looked at the graph a minute ago? Or now? What's true about the asymptote? What is it? It is a line, right? Remember I said we draw it as a dotted line? So we have to name it as a line. Does that make sense to everyone? So we call it its line name, not just a number. What's up? Yes, ask me.
On number 3,
yes?
if it says negative x, would that mean the numerator is -1 or just a 1?
Only the exponent. We only look at the exponent. Thank you. Okay, we only look at the exponent. Okay, the negative would come into play if these both happen to be the same. Then my asymptote would be a negative number. Okay, good question. Everybody okay so far? Please look at the worksheet that I gave you called vertical asymptotes. Okay, on vertical asymptotes, again, we're going to fill in these tables together because of time, right? So let's fill them in together. This one's 2. This one is undefined. Sorry, vertical. Vertical asymptotes is what I'm on. You good? 2, undefined, 0, and 0.5. I'm just going to go to the next one below it. You okay with that? Negative 0.25, negative 1, undefined, 2, undefined, negative 0.25, undefined, 0.416. Second column, negative 2.5, negative 6, undefined, 8. Below it, negative 5, undefined, 6, and 3.25. And the last column, undefined, 0, 0.5, and 0.66. Last table, undefined, negative 1, 0.5, and 1. Okay? So we're going to start with 1, 2, and 3. because in my opinion, 1, 2, and 3 are the easiest to see. Would you notice, please, where the undefined is in the table? And see if you can find that number somewhere in the equation. Oh, you found the opposite of the number? Where did you find the opposite of the number? In the denominator. Is there a way we could use the number to get, or the denominator to get that number? What about that? Wouldn't that get me that number? So if I take the denominator and set it equal to 0, is that going to give me the undefined? Guess what the undefined is? The asymptote. Okay? But remember, we don't want to have to find a table every time. We want to find a shortcut. And the shortcut to find vertical asymptotes is to take the denominator and set it equal to 0. If I set this equal to 0 and I add 2 to both sides, do I get x equals 2? Is that where the undefined was? If I set this denominator equal to 0 and solve it, I add 6 to both sides, that's x equals 6. Is that where the undefined is? What about this one? I didn't tell you to look at this one because it's not as easy to see, right? But if I set it equal to 0 and I add 12 to both sides and then divide both sides by 2, is that where the undefined is? How do you find a vertical asymptote? Set the denominator equal to 0. Perfect. Okay, even number 7. If I add 4 to both sides, do I get -2 and -4? I do, right? Because if I add 4 to both sides, I get x squared. X squared equals 4. How do I solve that? Square root. What's the square root of 4? 2 and -2. Yes, we have the plus or minus, right? So I have 2 there. X equals 2 and x equals -2. Does that make sense? Yes?
Can you do the plus or minus 2?
Nope, I want you to write 2 separate ones because they're 2 separate asymptotes. Okay? Does that make sense? Normally it's okay to write x equals plus or minus 2, but since we're finding asymptotes, we're finding 2 separate asymptotes. I want you to write them as 2 separate asymptotes. Does that make sense? Okay? Now here's the deal. Look at the back. Okay? 4, 5, and 6 are the ones I had you circle, but I need us to look at number 8. What do I have to do if I have to set this equal to 0? Do you remember when we very first talked about factoring, and I said, it's really important that you get to know how to do this because we're going to be doing it all year? Well, today is another day in all year.
Don't you have to get it for the 7x minus 18?
I got to factor it. What multiplies to be -18 and adds to be +7? 9 and -2. When I set those both equal to 0, x plus 9 equals 0 and x minus 2 equals 0. When I add 9 to both sides, subtract 9 from both sides, and add 2 to both sides, what do I get? Very good. X equals -9 and x equals +2. So how many asymptotes did I have?
2.
Did I know that from the beginning?
Oh, yeah.
Yes, because it's a quadratic, right? Okay. Now the rest of these that I had you circle, oh, this one, won't I get 2 on this one?
Yes.
Yeah? Okay. So kind of crazy, right? Okay though?
Yeah.
So how do you find a horizontal asymptote? Horizontal, we look at the degrees, right? We look at the exponents, we look at the degrees. Is the numerator greater? Are they same? Or is the denominator greater? How do you find vertical asymptotes? Set the denominator equal to 0. Most of the time. Oh no, right? Oh no. Kirsten's like, oh no. Most of the time. Yeah, most of the time, because here's the deal. Here's the page I told you, right? Here's the page I told you. This is the back of our removable discontinuities page. We're looking at these problems back here. Actually, we're going to look at the top. Okay? If I have x squared minus 3x, do you see a common factor there? An x, right? If I factor out an x, do you see I have x and x minus 3? What do I have to do with the denominator? Well, I have to factor it, right? What multiplies to be negative 3 and adds to be negative 2?
3 and 1.
Close, right? Negative 3, positive 1. But what do you notice in the numerator and the denominator?
It's the same thing.
It's the same exact factor. When there's the same exact factor in the numerator and in the denominator, this makes a whole. It's a removable discontinuity, but the generic name is it's a hole in the graph. Literally, here's an asymptote. You can see that asymptote right there, right? You can see that asymptote right there, right? But look right here. There's a hole at 3 because that's a factor that occurs in the numerator and the denominator. So when you're worried about vertical asymptotes, you also have to be worried about removable discontinuities. You have to be worried about holes. If it's a factor that's in the numerator and denominator, that's a hole. That's not a vertical asymptote. There's still a vertical asymptote right here at negative 1 because that factor is still in the denominator. Does that make sense? So look here at problem number 1. Let's do this problem together. Okay. What do I have to do before I start?
Factor.
I need a factor, right? So factor the numerator. We got to factor numerator and denominator. Factor the numerator. What multiplies to 8 and adds to 6? 4 and 2. X plus 4, x plus 2. Now factor the denominator. What multiplies to negative 6 and adds to negative 1? And positive 2. What do you notice? Where is the hole? Where is the removable discontinuity? I still set this equal to 0 to find it, don't I? Where is the removable discontinuity? X equals what? Set it equal to 0. Negative 2. Where is the vertical asymptote? Set that one equal to 0. Try one more time. I'm being picky. X equals 3, right? And then where is my horizontal asymptote? Look at the degrees. They are the same. If they're the same, where do I look? So where is the horizontal asymptote? Y equals 1. Very good. Very good. Does that make sense? Yes? So how do you find horizontal asymptotes? How did we find this one?
You factor, then set it
Not factors, not yet, not yet. Good guess though, good guess. I look at the degrees, right? I look at the exponents. Are they the same? Is the numerator greater? Is the denominator greater? And I decide where's the horizontal asymptote based on that. These were the same, so I looked at the leading coefficients, and that was my horizontal asymptote. How do I find vertical asymptotes? Set the denominator equal to 0, unless that factor is also where? In the numerator. And if it's the numerator, it's also in the numerator. What is that? How do you say that? How do you say it? Removable discontinuities. But what's the shortcut way to say it? It's a hole. Right? It's a hole. It's a hole in the graph. It literally looks like that. Now, I'm telling you right now, it's not going to look like that on our calculators because our calculators are too good. It's not going to show a circle with a hole like that if I graph this right now. Okay? But you are smart enough to know that there is a removable discontinuity. There's a hole there. Questions? You got it?